All right, guys and gals, this lesson that we're going to deal with is in our unit, but it is not in our textbook per se. All right, it does cover area of different polygons in another chapter, but I didn't want to cover all the different polygons that are out there. I just wanted to deal with quadrilaterals. So what we're going to look at today is the area formulas for our quadrilaterals, what I call how much is in the middle, because we're not looking at perimeter, right? We're not looking at the distance around. We're looking at the area on the inside. So we'll go over those formulas, talk about how to derive them, how to get them out of thin air, and then we'll go from there. So take a look. Let's review real quick just what the basic idea of area is. When we're talking about area, we're not talking about a linear distance, all right? So we're not starting here and counting 1, 2, 3, 4. That's not what we're doing, okay? What we're doing is we're looking at a square of a particular size. So let's pretend that the square is, I don't know, 1 inch by 1 inch. It's not, but we'll pretend. When we're finding the area of a figure, so for example, if I wanted to find the area of this triangle, what I'm trying to figure out is if I were to take that 1 inch square, I want to see how many of them it would take to fill in the figure. And notice some of our squares would be whole, some of them would be partials, but in the end, we would take all of those different squares, add them together, and that would give us the full area. Now, area formulas, for example, the area formula for a triangle is base times height. So in other words, I would take a linear measurement, so in this case, the base measurement, multiply that by the height, okay? And then in this case, our formula would tell us to then divide by 2. Notice if I wanted to find the area of this figure, I would just simply take base. So in this case, my base would be here, and multiply it by my height. All right, so this distance here. And because I do that, I'm taking two linear measures and multiplying them together. Our result is what we call a square unit. So for example, if this is inches, 1 times 1, so that would be 1 inch square, because I'm talking about that actual square unit, not a linear measure. Or here, let's pretend we've got about, I don't know, we'll call it 4 across. So maybe our base is 4 inches across, and then our height, I don't know, 1, 2, 3, 4, we'll call it 5, is 5 up and down. So that would be 4 times 5 divided by 2. Well, again, one linear measure multiplied by another linear measure gives us that square measure. Again, one by another. So 4 times 5 is 20, divided by 2 is 10. So in this case, we would have 10 inches. If I could write, there we go, 10 inches squared. So all of the units that we're dealing with today are square units, right? How many squares of a particular size fit into it? Whether it's square inches, square miles, whatever, we don't care. So heads up, make sure you know that. Let's look at our quadrilaterals and see about these different area formulas. So let's start off with squares, rhombi, rectangles, and parallelograms, because they are all technically parallelograms. So they're all going to have the same area component. Here's how we do it. As we just saw with the square, we have what we call our base and our height. If I take base times height, that will give us our area. All right, in this case, our square area. Well, let's look at a rhombus. Notice a rhombus is a little bit different. With any rhombus, we can take a perpendicular to both top and bottom here and run it down. Perpendicular top and bottom, run it down. And notice these two triangles would have to be congruent. So for example, if this distance is, say, A, and this distance is, say, B, well, notice we'd have that same AB distance down here all together. So again, the overall base times the overall, again, another base. And then the last thing we need, of course, is the height. And notice the height's the same no matter where we are. So just because we've got triangles here, I could move this triangle, put it right over here, and notice it's still B and A, same distances. So the entire base times the height. In other words, we can take that rhombus, transform it into a square or rectangle, and we're good to go. So for here, same area formula, still base times height. Rectangles, same way, base times height. And parallelograms. Parallelograms, just like rhombi, we can take these triangles shift one of them over, and suddenly now the area I'm dealing with is, say, a rectangle or a square, depending on how it was worked out. So again, still base times height. Now, a formal proof for that. All right, well, let's talk one through. Again, we won't do it super formal, but we'll get one sort of informally done. We'll use a parallelogram as our guinea pig here. So again, we'll give this entire distance across the bottom as b. All right, our height, of course, is the perpendicular from top to bottom. So how do I know that those two ideas are going to give me this overall area, even though we're on a slant? All right. Well, notice we could rename this, and I'll use something other than a b here. Let's use a and c. So the distance from here to here is a, distance from here to here is c. Let's draw another perpendicular here. So we know this has to be c. How do we know that this other has to be a? Well, first we know that those opposite angles of a parallelogram have to be the same. So this angle and this angle we know are the same. The height, since our sides are parallel, these have to be the same. And notice these sides, opposite sides are the same. So those are the same. Right angle, right angle. So we can do a side, angle side, 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 side. We've got all kinds of options here. Since it's a right angle, I would propose that we use side, side, angle. Again, we said we can't really do that, but since it's a right triangle here, we can do that with Pythagorean theorem. So if this distance is a, this distance is a. So by simply moving it over, notice this entire b is still the same b that it is here. By moving this triangle over, still that distance a and c, a and c. So again, base times height. So again, not fully formal, but it gives you an idea of why that formula works here, just like it would work for, say, a square or a rectangle. Now, here's something new that maybe you've never seen before. If we're talking about rhombi, all right, so squares in particular, and then just general rhombi, here's another area formula that you can use. And this is a good one to know. And it's based on diagonals. So I'm going to call this diagonal 1. We'll draw the other one in. We'll call this diagonal 2. Now, notice, for all rhombi, their diagonals meet at right angles, right? We've proven that already. Let me go ahead and draw this one in too, since we're at it. So again, we'll call this diagonal 2 just to keep the color scheme the same. And we'll call this diagonal 1. And again, they meet at right angles. Cool. So let's look. I'm going to grab just one of these triangles. So I'm going to grab this bottom one. So it right now looks something like this. Half of diagonal 1 is here. So diagonal 1 over 2. Half of diagonal 2 is here. So half of diagonal 2. If I wanted to find the area of that particular triangle, well, I would simply take base times height. So d1 times d2. 2 times 2 is, of course, 4. So base times height, and then divide it by 2, and that would give me my area. So in other words, one of these triangles is worth d1 times d2 over 8. All right, well, notice there's one of them. I've got 1, 2, 3, 4 of those, because all of those triangles end up being exactly the same. So I can take that, multiply it by 4. Well, 4 over 8, well, that's a fancy way of saying 1 over 2. So d1 over d2, 1 over 2. Cool. There's our area formula. Another way to talk about area of rhombi is to take the diagonal multiplied by our second diagonal and divide by 2. So again, there's kind of an informal way of proving it and how it works. Obviously, for this rhombus, it would work exactly the same way. The only difference is obviously our diagonals here are identical, whereas here they're a little bit different, but our formula allows for that. So again, something to think about. Let's talk about trapezoids, by far the weirdest of our quadrilateral shapes. Let's talk about how we would find that area. We've got an isosceles trapezoid here, so we'll go ahead and label it as such. This is isosceles. This one is not, all right? I purposefully made this one a little bit different. Let's start with the isosceles trapezoid. Notice we have two different bases, so let's go ahead and name them. So this is base 1, and this is base 2. We're going to do a same trick here that we tried back here. We're going to lob off triangles. So for example, if I were to lob this triangle off, and we'll go ahead and mark this one in as well, I can take this triangle, flip it around, and put it over here. So notice what would have happened. That means this longer base got a little bit shorter. This smaller base got a little bit larger by the exact same amount. So here's the formula, and then we'll talk about, well, how we could derive that. So the formula is base 1 added to base 2 divided by 2 times the height. Focus on this a moment. Base 1 plus base 2 divided by 2. That's an average, right? That's a mean. I'm finding the average length of the base. And notice what we've done. We've taken a little bit from one, the longer one, and given that same little bit to the bottom, so that way they're the same. If we're finding averages, that's pretty much what we're doing. For example, if you got, say, an 80 on one of your exams and a 90 on another exam, and let's say those are the only 2 grades you have in the whole class, well, to calculate your grade, a teacher might just add them together and divide by 2. We're going to take a little bit from this one and give it to the other. That way they're both 85. Well, that's exactly what we've done here. We've taken a little bit from this one, added that same little bit to the other, and now they're exactly the same size. So the question is, how do you prove that? All right, well, let's try it. So notice our 2 triangles, because this is isosceles, are going to end up being exactly the same size. So we got base 2. This overall is base 1. But notice, they've got sides the same. They have right angles, because again, our heights are made with perpendiculars. We know the sides are the same. We know these angles are the same. And of course, the fact that they're right triangles is even better. So we know that they are similar by 2 angles, but because of this side, and of course the height sides would be the same as well, we can do it by angle, angle, side, or angle, angle, side, either way. So these are identical. So I could say that this distance here is B2, and then these distances are something else. We'll call them A. So by moving this over, let's redraw the diagram. I end up with B1 up top minus an A. I end up with a B2 here at the bottom with an extra A added on. Right? Because this was B1 and it had one of its A's removed. This is B2 with one of the A's tacked on. And notice, B1 could be rewritten as B2 plus 2 A's. Cool. Well, I just took one of those A's off. So B2 plus A, B2 plus A. Cool. And then, of course, multiplied by our height. So that gives you a kind of informal way of proving that. Let's take a look at this trapezoid. We could do basically the same thing. The only difference is we know that these 2 different angles are different, right? This is a non-isosceles trapezoid. So one way we could do it is when we cut these triangles off, instead of simply moving one to the other, here's one way we can do it. Okay, we can cut the triangles along a mid-segment, flip this up, flip this up, and then take this remaining rectangle and just simply slide it over. We end up with the exact same deal. We get 2 bases that have simply been averaged out with our heights, and it works the same. So, quick review. If you've got, there we go. If you've got a parallelogram, I say, no, that didn't look right. Then our area formula is base times height. All right, and that works for any parallelogram. All right. Specifically, though, we said if you have rhombi, so that includes a square, then we said another way to write their area formulas is diagonal 1 multiplied by diagonal 2 divided by 2. If you have a trapezoid, then we said the area formula there would be base 1 added to base 2 divided by 2. So again, giving you that average multiplied by your height. All right. The only other figure we really haven't touched on this year, and we'll talk about it here in these last couple of minutes, and it's if you think trapezoids are the kind of the red herrings of the group, then you haven't seen anything yet. This figure is known as a kite. Here's what makes kites special. They have two pairs of adjacent sides that are congruent. So you end up with something like this. What's interesting about kites is that not only are those adjacent pairs congruent, which gives you this, again, what we call a kite shape, the diagonals, because of that, will meet at a right angle. All right, well, which other figure have we talked about that does that meets at that right angle? Well, rhombi do that, right? Squares and rhombi meet, those diagonals meet at a right angle. And as it turns out, kites share the same area formula. So if you do see a kite in our work, area is still the same as a rhombi. Diagonal 1 by diagonal 2 divided by 2, and you're there. Again, make sure you bring any questions that you have about what we've done here to class. We'll talk about it. The other thing that we'll talk about in class today is your proof project, specifically about Unit 4/5, any issues that you're having with those. Bring your questions and we'll talk them out. All right. Have a good day, folks, and we'll see you in class.